Okay, let's get started with the afternoon program. We're going to look at one of the frameworks in the WebGL stack that I personally work a lot on, luma.gl, and the next version. You've already heard a lot about it and the kind of central role it has in the enablement of WebGPU for the rest of the stack. About me, my name is Ib Green. I'm an engineer here at Foursquare. I have worked with these frameworks since the very beginning in 2015. So it's going on, I guess, almost 8 years now. So really excited to see all of you today, see this community has grown and still vibrant and alive. I worry a little bit. It's really a topic that I'm passionate about, but I'm also, everyone just came out of lunch, digesting our food, and it's a little bit technical. I try to make it interesting. Normally we talk about DECGL and Kepler and the kind of showcases of our framework suite. I guess many of you, from talking to you and shaking hands and meeting with people here, are using DEC. So you know DEC pretty well. You probably know it uses Luma. You probably don't know too much about Luma because you don't really have to unless you're doing really custom layers and extensions. So I'm going to kind of go a little bit into the kind of a brief overview of Luma, and then obviously talk about what we're doing with WebGPU and why the heck it's taking so long, and a little bit about the impact on DECGL. We've had a couple of perspectives on what WebGPU is. I would make these remarks. It's a generational upgrade, hopefully. So once in a generation, WebGL is API, OpenGL API is probably 25 plus years old now. And so it really was outdated, in enormous amount of versions and extensions. It ended up very messy, and something new was needed. The WebGPU API is something of a compromise. It's a kind of a common denominator of a number of next generation GPU APIs. And so Metal from Apple, Microsoft Direct3D 12, and then you have Vulkan more on the Linux side of things. And so while it is an API in the style of these next generation GPU APIs, it's also an API that really, only deals with a common subset, though it does allow for extension. This approach has allowed repeating some mistakes that WebGL 2 suffered from, where some vendors, for instance, Apple, were, very much against adopting a spec they felt that was out of their control. And so hopefully this will mean that we will see really strong support on all devices. We've also, I think, touched on the fact that WebGPU is not browser specific. While the WebGPU standard is a W3C standard, the spec can really be thought of as an IDL, an interface description language. And so WebGPU can be implemented in any programming language. And so Dawn is a native implementation in C++. I believe it is used by browsers like Chrome to implement WebGPU. There's also Node.js variants already. It's pretty tricky to use WebGL in Node. You have to use like headless GL and stuff. But there are Node.js variants that already support WebGPU natively. And obviously Rust bindings and any other language, native language. All right, so the luma.gl is a little bit different than other, let's say WebGL or WebGPU kind of libraries. And, thinking about maybe 3JS, Babylon.js, who focused more on the maybe game programming model for 3D rather than the visualization model. And they tend to have a little bit more magic. 3JS, I haven't worked with it for a number of years, but when I did, it had like a renderer class, and it took these abstract meshes, and then it did all the magic under the hood. It created the buffers, and so it did both the kind of GPU handling, but then also did things that we see more as the responsibility of DECGL. And so luma.gl was always modeled to be very close to the GPU API. And so luma.gl, the earliest version was WebGL 1. luma.gl, I think before V5 onwards until V8 was, which is the current version, was based on WebGL 2 API, and the new version that's coming out now that we're working on is modeled to be very close to the WebGPU API. And so it's kind of an idea about the feeling. If you work with luma.gl, you kind of almost feel that you're working with WebGPU. It's a little bit less verbose. But under the hood, you have like full control. There is like no magic going on. And so obviously, by choosing this, we had to make a big breaking change now, because it makes no point if our primary target is WebGPU to have an API that's based on WebGL. And so, but again, hopefully this is a once in a generation upgrade. We don't have a completely new WebGPU type API in the next couple of years. And so this is the module structure in brief. So it's really kind of three main modules. There's a luma.gl core, so it's a monorepo, and so it's like most of the deckgl, mathgl, loaders.gl, and so on. We follow this system that we have a core module. So we use this scope namespacing. It's sort of npm modules. You can just yarn install or npm install. There's a core module, and there is then an engine module and a shader tools module. And so the core module now, the new thing is it defines an abstract API, a portable API for working with the GPU resources. So how do you create things like GPU buffers, textures, shaders, programs, or pipelines, as they're called in WebGPU. And then on top of that, we have what we call the engine layer, luma.gl engine. It has higher level constructs, but they're written completely on top of the core API. And so they're kind of insulated from whether you run on WebGL and WebGPU. And the canonical class is model, all the deckgl layers uses that. There's the animation loop, geometry, scene graph support. Still pretty basic stuff, but it's kind of in a separate layer. And then we have a pretty extensive textural shader processing system, and that's in the shader tools, also with a lot of shader modules. And so the kind of new thing here is that the core is no longer bound to WebGL, but completely portable. And then you have to install one or both of the backend modules. So you can install luma.gl WebGL, which I believe deckgl is going to do by default, and that means that the WebGL backend is there, and then you can install luma.gl WebGPU and add support for WebGPU. We're going to look a little bit on how that works in practice. First, we're going to take a look at luma.gl engine module, and I'm not going to go into this detail, but again, we're keeping the engine layer separate, and that keeps the lower layer that accesses the GPU very clean. We don't get a lot of thick logic in there. So this is a model that works out quite well for maintainability. And the model class is really where everything comes together. So, you can work without it, but if you have a couple of shaders that need to be, compiled into shaders, linked into a render pipeline. You have lots of uniforms or uniform buffers in WebGPU. You have bindings to those uniform buffers, textures, samplers. You have attribute with all the long GPU buffers that power the binary columnar data, if you will. You have all the GPU parameters, and there's also then the all the shader assembly that goes on if you want to use luma.gl shader modules and so on. And all of that comes together in the model class. So that's really the workhorse that you would normally use. And then we have our shader tools with the shader assembler, and it basically handles injections. So you can inject custom code in shaders. deckgl uses that to powerful effects. If shaders and modules are written in different GLSL version, it automatically transpiles them, and so it does quite a bit of work. And it's just available through a simple shader. You instantiate the shader assembler, and you can do and assemble shaders. And then the other thing that this module has is a quite large list of long list of shader modules, pre-built, pre-tested shader modules that you can just include. So in your own shader, You can either, projection picking, lightning modules, even PBR for like GLTF caliber, materials and so on. It's available as shader modules, and then there's a lot of post-processing where you can, apply effects on the screen after it's rendered. All right. So now we're going to take a bit of a look at how do we achieve GPU portability between WebGL and WebGPU. And so this is where the kind of portable or API and luma.gl core comes into play. It needs to be used with a backend, and today there are 2 backends. It is, in principle, possible to imagine another backend, but likely that would require additional work on the core API. The way an application interacts with the core library is you need to get hold of a device, an instance to a device class. And once you have, and that is going to be, that's an abstract, an interface, if you will. And so where you're going to have under the hood is either a WebGPU device or a WebGL device. And on this device, you now have all these methods to create GPU resources, buffers, textures, shaders. And if you have a WebGPU device, it creates its WebGPU buffers and WebGPU textures, shaders, and correspondingly with WebGL. And so you can do all the things you want to do with, a rendering context or a device. You can get the limits of the device, what's the biggest texture you can use, and all that. You can get a list of features. There's portable feature strings. You can check which texture formats are supported. Is that format renderable? Is it filterable? And so on. How do you handle device or context loss and so on? All the stuff, you would do in a WebGL context, you now do in device class. I think this similar code snippet was already shown in the keynote, but it basically shows how do you go about, how does an application go about this? Well, you import your the backends you want. You import the devices, you register them, and then you can use luma.create device. And if you use the type best available, it's going to pick in this order. So if the WebGPU is supported by the browser and the WebGPU backend is installed, you're going to get the WebGPU device. And otherwise, if WebGL2 is supported, you're going to get the WebGL2 device and so on. And you can, of course, do explicit selection as well. So you can specify the type that you would like to use. So now that you have a device, what can you do? Well, again, you have all these GPU resource creation methods that return different things depending on which backend you're using. And so the device, as we see, it's used to create other resources. A new concept is canvas context. So in WebGL, you can really only draw one canvas. The WebGL context is very connected to the canvas. On the WebGPU, you can draw to multiple canvases or none. You can just open a device for compute. And so to manage that, there is a new class canvas context. You can only obviously have one on WebGL. And then the 2 things applications would do mostly is creating buffers for memory and textures for memory that is arranged in either 2D or 3D, 3-dimensional layouts. Then the render pipeline, that's the linked shaders that you use to render a shader is a single compiled shader source code. A render path basically records rendering operations. So to do any rendering, you need to create a render path. A frame buffer is really just a helper class that contains attachments that the render path is going to render into. So you typically render into texture, a color texture, maybe a depth buffer. And there's a new compute pipeline that is available on WebGPU, but it's not available in WebGL. WebGL uses something called transform feedback. We're going to come back to that, but that's one of the many big differences between WebGPU and WebGL. How do we do compute? There's a command encoder for allows you to do things like copy buffer to buffer, texture to texture, and so on. You can, and there's a vertex array to store all your binary columnar data for the render. So looking at the luma.gl WebGL module then, which is the backend, right? This is really where a lot of the work has gone in, right? So really the question here, a little bit sarcastically, how many ways can you break the WebGL API? WebGPU has really noble goals, but backwards compatibility was not among them. And so just a few examples. Each of them, some of them are small, some of them are big. Together, it's really kind of a knockdown blow. So they have a completely new shading language, WGSL, which means that all our shaders, both in Luma and DEC, have to be, rewritten. They don't support individual uniforms, only uniform buffers. It has advantages, but it's much more structured API. It requires, it's much less, requires more work on the JavaScript side to work with it. And we already mentioned no transform feedback. Now we have the new compute shaders, compute pipelines. Contrary to what you would think, things like vertex, the kind of vertex attribute types, the binary columns that you can give to the GPU is much more restricted. GPU resources are immutable. They can't be changed after you create them. Like all the GPU parameters, like, whether you have depth testing on or, culling and so on, they're frozen on resource creation. They can't be changed dynamically. You don't have constant vertex attributes. And so many things that both Luma and DEC have relied on have kind of been taken away. The upside of all of this is, of course, an API that requires a lot less validation because resources are immutable. They don't have to be checked every time you kind of supply them. And so overall, the promise is that the performance should be better, much better. I'm not going to go through this, but this is just maybe half the list of things that we discovered while porting making the model class work on IndexGL v9. Many things that we took for granted that you could do with attributes in WebGL that WebGPU doesn't, at least as far as we can tell, doesn't support. So yes, it's been a very big effort. The code base has been rewritten, like most of this GL, to completely leverage TypeScript. It makes a huge difference when we refactor things. And implementation has been dramatically simplified, cutting away things that are not needed for WebGPU. We're gonna be in a world where we maintain 2 backends, and the source code is gonna need to be squeaky clean, easy to understand and maintain. The downside of all of this is we completely lost backwards compatibility with V8. All right. So do I still have your attention? Probably not, but I'll give it a try. All right. The elephant in the room is shaders. So we already mentioned that we have a new shading language. We've been building up a sophisticated shader assembly, shader module system on top of GLSL. Well, now we have, initially it looked like WebGPU was going to support GLSL 4.5 or perhaps binary shaders in Spur 5 format, but in the end, they went with a new shader language with Rust-inspired syntax. And it's highly structured, much more structured than GLSL, at least in the early versions that WebGL uses. And so everything needs to be explicitly declared, every binding points and so on. The type system is more explicit. Feature-wise, it's obviously similar to the latest GLSL. And so that's good. We get a lot of new features in the shaders, but still, there's a lot of differences, and there's no way we can automatically transpile our current shaders. That simply, these shaders need more information that we don't have in our current shaders. The exact binding points and so on. So for the initial version, we're going to have to support 2 versions of each shader. So we've extended the model interface in a couple of places, shader assembler and so on. Now, wherever you specify the source code for the vertex shader and the fragment shader, you can provide an object with GLSL and WGSL fields, and so you can provide duplicated shaders. To address this more long term, we've been, brainstorming about could we, we obviously want this to be, we want luma.gl to be the API where you work with the most modern, WebGPU techniques. So we probably, if we're going to pick one language, we would probably pick WGSL then. And so could we then automate translation from WGSL to GLSL? The answer is probably yes, because there's a lot of information in the WGSL. However, we would need a parser for WGLSL and set up all these rules. So it's a fairly big effort. Interestingly, there are some open projects that seem to do similar things. There is a project called Naga, I think it's written in Rust, that transpiles between different shader dialects. I think it also covers probably also covers metal shaders and Microsoft formats and so on. But it's tricky for Luma maintainers to have to work across multiple programming languages and code bases and so on. So we don't really have a conclusion there. Okay, I think if I lost you in the details inside Luma, then I think most of you will be more interested in what is the impact on DECGL and your applications. What are you going to have to change when you upgrade to DECGL 9 and you eager to test things on WebGPU? So I can't give the full list here, but I can just paint the picture. So GPU parameters are now the WebGPU style. They're strings. So that must be updated. The strong typing that helps with that. The texture class API for the layers that optionally accept textures has changed a bit. The binary attribute support. Some of the things that we may lose initially in maybe the 9.0 version to pass in binary attributes may not be possible in all cases. Transitions may not initially work on GLTF, scene graph layer may not be available initially. We haven't made decisions on it, but it's efforts that we would have to make. Post-processing modules may not be available. Some of the extensions that Felix talked about may take time to port. And one thing that's pretty clear is that we will lose WebGL 1 support. So I just talked to someone here in the community who heard a loud scream from Microsoft when they removed WebGL 1 support. I guess there are still Internet Explorer 11 users out there, so we'll see if that history repeats itself. But because of the uniform buffers, I think it'll be a lot of work. I'm not sure we'll put in that work to support that. But there's also some improvements. I'm not going to go into the details. You no longer need to import constants. They're just modern TypeScript strings. All right, I'll give you a little bit of the roadmap, and I thought this was just maybe a fun slide. So, like the effort, I made it kind of a little bit silly back on the napkin chart where this is the effort that's going into the WebGL ecosystem. I guess it peaked here, 2018 maybe, when Uber had a really big Viz team working on it. And then, what are the features we're getting out of it follows that curve, pretty well. Then, we kind of broke out from Uber, and then we had, Kato and Foursquare and S3 and Action Engine. The community picked it up, and we started to get, acceleration again. But then we've seen, I think, in my view, or at least it's kind of how I feel, we've seen the features lag behind. And first we had this, we decided to rewrite and refresh the tech stack, and everything was written in TypeScript. And now we've had this WebGPU porting. So what we're basically saying is that there is a tremendous amount of cost being, effort being sunk into this framework, but we're not really seeing the kind of benefit. And hopefully then, now that WebGPU porting is done and everything has been moved to TypeScript, we should see a landslide effect, and we should really start seeing exciting features. What might those be? Well, we talked about the shader transpilation system. That'd be great to see. Obviously, we want to really work on this, like the WebGPU compute shaders, and probably create new features, new extensions with that, and maybe not worry too much if they will work on WebGL. I think I answered in one of the questions. We want to have really good optimized to the bone support for binary columnar data, so that we can load even bigger data sets even faster. You know, we could see us GLTF standard for the scene graphs. They has evolved quite a bit. There's a lot of amazing new material, you know, attributes, clear code, and you know, you can model fabrics and other things. Be nice to include those. Keep updated with the latest texture and geometry compression formats via Loaders.gl. And so those are just some ideas, but there's a lot of things we can do. And maybe next year, hopefully we'll have another Open Visualization Summit. I'd love if GPU compute was the headline, and we would bring together all, you know, different examples of how we've taken this to the next level now with WebGPU, and also with CUDA, which is going to be a talk that follows.